Great, thanks a lot, Jim. Our speaker tonight is Tom Palakis. Tom was an aerospace engineer at Honeywell for over 30 years. He has been an amateur astronomer for 43 years and has written for both Sky and Telescope and Astronomy magazines. He's also been the co-author or the author or a co-author of 25 papers in refereed journals. He's now an observer and research assistant at Lowell Observatory in Flagstaff, Arizona, and is interested in visual observing and imaging. Live from Tempe, Arizona, please give a warm virtual welcome to Tom Palakis.
All right, thanks, Mark. Hope everybody can hear me okay and see me. I'm going to go right to the slides here. I'm going to share the screen, sharing that one, making it big, and it should be right there. Okay, so I wish I was a research assistant at Lowell Observatory. I got hired almost exactly a year ago and to work on a 42-inch telescope up there. And then the camera broke immediately, the cooler on it, and getting the parts for it was almost impossible. And they got it all back together just in time for the pandemic. And so now Lowell is having only one telescope operator on that telescope as of last February. So nominally, I'm still a Lowell employee, but it's just going to have to wait till hopefully things sort out here. So what I'm going to talk about is photometry, and hopefully you haven't seen many talks about this subject. I was a mechanical engineer. I worked in the aircraft engine industry, and with a love for astronomy since I was a kid, like most people in this club, I'm sure. And I couldn't wait to retire and get out and do astronomy full time. That's kind of where I ended up here. So I did technical work, a lot of modeling, data analysis, that sort of thing at the computer. And that's what I was comfortable with. And if I had just stopped doing that when I retired, I was fortunate to retire at 54 and a half years old, almost 5 years ago now. If I had just stopped doing that, then my mind would have gone numb. So I had to continue with it. And so the idea was, let's get into the kind of technical side of amateur astronomy. Whereas before I was primarily a visual observer, which is still a lot of fun getting out into the desert and observing. And that's what this talk is going to be about. So I live in a big city, 4.5 million people in the metropolitan Phoenix area. And Tempe is not at all separated. It's right in the middle of all that population. I can barely see the Cygnus Milky Way overhead with averted vision. And so I'm losing 2.5 magnitudes or so to light pollution. So what you can do with a camera from the city, one thing is you can get a hydrogen alpha filter, which I've done a lot of this, and do narrowband images. This is a little piece of the North American nebula. Another thing you can do is tricolor, just aesthetic imaging, which will be very compromised by the brightness of the sky. And a third thing that you can do is measurements, and that was my attraction there. And I'll talk about these 3 different types of measurements, which are listed in ascending order of difficulty. So one of them is just astrometry. Done a little bit of this, not much. And that's typically if you find a new comet or an asteroid or even supernova, that type of thing, any type of transient object, you want to get an accurate position of it down to even thousandths of an arc second if you can. And that's measuring positions of objects. Next up is what my talk is about, is measuring the brightness and color of objects. And I know several people in the clubs here in Phoenix, actually 4 or 5, who do spectroscopy. That's the most difficult. And what you get from them is velocities, like your radial velocities, and you get the molecular composition. And far and away, I think you get the most information out of spectroscopy. And I've shied away from it, and I'm just doing photometry as my type of measurements. Photometry, if you look it up in Webster's dictionary, there's the definition up there, which says you're just measuring the intensity of light. For astronomy, that is almost always done versus time, so over a period of time, and that time can be just real short periods, and it can help to go out and be in it for the long game and do it for decades of doing these measurements. So when you're done with it, you end up with the illustration there, and that's called a light curve. So I'll keep talking about light curves throughout this talk, and there will be two types that we'll go through. So first, I have to kind of show you the method of how do you measure the brightnesses of stars or asteroids. How do you measure these things? And we'll start with my mechanical engineering explanations, since I'm real bad at electronics and I still don't really understand how a CCD detector works. I look at it when I see 6 megapixels, 6 million pixels. I think of each pixel as a cup, and water is going to flow into those cups. So think of starlight as just filling these cups with water to a certain extent, depending on how fast the water is flowing. So exposure time would be how long you leave those hoses running, and it's like just measuring the amount of water in each one of these cups. So a couple limitations: if you only have a couple drops of water in a pixel or in a cup, drops of light in a pixel, that's going to be really hard to measure. And if you have too much and the cups runneth over, you got problems there, because you can only say that it's at least this bright. And I'll go into that in this slide, which is saying that each pixel on a chip has a depth to it, if you will. And I'm putting the number 48,000 out there as full. It's not really full, but we'll use it for the purposes of this talk. And they call these analog to digital units. So you just have a number, black is 0 and white, pure white, is saturated at the top of that end. And again, I'm using 48,000. So at my site, I do a 2-minute exposure and the background sky is bright. So I get 4,000 to 6,000 ADU. And we want to make sure that our target, we want to expose long enough so that we're above that significantly. So we're not just barely above it, we want to be significantly above it, but we don't want to be too far above it so that we're getting saturated results. And so that's where you end up trying to set your exposures and learn what are appropriate targets that I can actually go after from my backyard site. So here's a negative image of just a star field, kind of a random star field. And we'll look at 3 stars in this image just as an example of what I'm talking about. So star 1 up there, really bright star. Star 2, medium bright, just right. And star 3 is that very faint one inside of each of those rings. Kind of a busy way of presenting it here, but here's star 1, this real bright one. And here's a profile of that star. And what you can see is the cup of water has spilled over. There's a plateau at the top here. These are 8 by 8 pixels and 49,000. You can see that all these numbers are about the same. And that means that it's too bright and you're not going to get a good measurement out of that. You'd have to shorten the exposure in order for this to work. Here's a just right star where you're at about 30,000, 20,000. And that's the kind of measurement we want to make, is of a target that's about that brightness. And finally, here's what happens if you make a profile. When you have something that's, say, in my case, 16th magnitude, something pretty faint for my setup to measure, the sky is going to be so noisy compared to that little peak sticking up for star number 3 that it's going to be, the errors on that measurement are going to be very large. We call this aperture photometry, and anybody who's used a telescope knows about telrads, and this looks a lot like telrad rings, but they're not. And what you're trying to do is put the starlight, all the energy, or the asteroid light, whatever you're measuring, inside of this central aperture right here. So in that last slide, I showed that profile of a just right star rising above the noise floor, and you put an aperture around that star. So you wonder what the other rings are. Here's that aperture that you're going to measure the brightness in. And then there's just a dead zone to separate it from the sky brightness. And so what you're kind of doing with these measurements is you're doing signal to noise. You're saying, here's what the brightness of my object is, and here's what the brightness of the background sky or the foreground sky is. So if I just measured the brightness that way with no references, it would be kind of a meaningless thing. You'd be able to see the changes, but you wouldn't have it on a scale of magnitudes that we're used to. So what you do is you choose, in this case, and it's an ensemble of comparison stars. These stars are stable, they don't vary if we picked them right, and we know the brightnesses in different colors. We know the brightnesses real well, so we're going to compare this against these 4 comparison stars, and we'll be able to make a light curve at the end of that. So here's a light curve. This is a variable star. It's called an RR Lyrae star. That's XY, XZ Cygni. And then here's our 4 comparison stars down here, and they're flat. So that's the way you kind of go through this, is you have to, for any time you have a field with a target, you want to pick the target, and then you'll pick several comparison stars. And there's a little bit of an art involved in doing that. So what does a sunset have to do? And man, this is the right time to talk about this with the red sunsets. We've had averted vision sunsets where it disappears before it goes through all the smoke over California and over Arizona here. So we've had these very red sunsets, and the sun's not red when it's near the meridian. And the reason for that is that the atmosphere is dimming the blue wavelengths more than the red wavelengths. And that has a lot to do with photometry, because what you're typically doing here is you're following these targets for 8 hours, 10 hours for an entire night, maybe multiple targets, and they're going to rise. They're going to be 20 degrees off the eastern horizon. Then they're going to go to not necessarily the zenith, but that's what I'm drawing here. They're going to go as high as they get, and then they're going to be low again. If I picked comparison stars that are blue and my target is red, we'd be in trouble, because we have a difference in the way our Earth's atmosphere is affecting those stars. Since the blue light is going to get dimmed faster than the red light, that's going to make a mess of your photometry. So you also have to pick targets that are the same color as comp stars that are the same color as your target. So the answer is to move your telescope out into orbit, which is not really practical. Finally, speaking of color, here's the different filters that you use. You can't use, for kind of pretty picture aesthetic imaging, you use these red, green, and blue filters. So in this case, in photometry, there's very specific filters that you use. These are ultraviolet, blue, visual red, and infrared, with the kind of the band passes shown here. So what that does is allows you to be on the same system. When I say I measured a B magnitude or a V magnitude, that's the same system that they're using at Kitt Peak or Paranal or at a real observatory. There are a couple newer ones that have been introduced since this system, but you can transform over to them. So we end up with these very specific filters, and since they're so specific, interference filters, and they're hard to make, they're also expensive, like everything else is in this hobby. So I've kind of raced through that, hopefully not too fast. And now I want to just talk a little bit about my observatory and my site and what I used to do versus what I'm doing now. Now, when I first got started setting up an observatory, I bought one of these sky tents, which is an obsolete company. And the Arizona sun, after 3 or 4 years, will just completely take one of these things out, as I learned the hard way. But it was good while it lasted. I had a 10-inch on a Schaefer mount at the time, and I did a lot of planetary imaging. And I'm doing it again out in my front driveway with a completely different setup. But this is what type of stuff that I did while I still had a job, and still had to go to bed at 11 o'clock or something. So now I'm not so limited. And as I've said before, my goal at retirement was going to be to do photometry and get this thing up permanently set up. And so what I did when I retired and had a nest egg is I didn't purchase a red sports car. What I did instead was started building an observatory with my friend Mike Collins. Mike did about 75% of the work and 100% of the design work, just being a nice guy that he is and really competent. And so what you have here is the first incarnation of that observatory, which looks super clean compared to the way it does now. It is on an 8-foot by 10-foot slab with an 8-inch pier near the center of it. And several instruments have been on that pier since then. This was the original one, was a C11 on that pier. It's funny to look at how clean everything looks there now. So that's the backyard observatory, has a pretty good view of the sky. And here's the equipment that's currently in the observatory. That's just my old solar scope, which has been replaced. It's a 12.5-inch, it's called a Dahl-Kirkham telescope. They have these gigantic secondary mirror. It's a 6-inch mirror. It's a 50% central obstruction. So it's not very good for viewing visually as planets. It's kind of a low contrast scope that way. But what it does do is it's corrected over a full 1-degree field all the way to the corners. So the stars don't look any less sharp in the corners than they do at the center. And that's what you want out of an imaging telescope. The camera, which is hidden behind the filter wheel here, is an ST6003 from SBIG. It has taken, as I'll mention, it's in 6 figures. It's taken about 125,000 exposures now, which is part of what happens in photometry is you take a lot of images. The mount is from Italy, a company called 10 Micron, has one of the original companies that put absolute encoders on the mount. So you can unlock the axes and move the telescope around and it still knows exactly where it is. It's amazingly reliable mount. It just will not fail. And it has been in a lot of extreme temperatures and has gone real well. So my wife was good enough to just say, spend the money, quit getting frustrated, quit coming into the house and using these 4-letter words about the equipment and get something that works and don't buy a sports car. And so there's the inside of the camera, in case you're curious, and the filter wheel, and I had it taken apart. The filters are 2-inch filters. There's a luminance, which is a clear filter, ultraviolet, which I've since removed because I can't see anything through it, B, V, R, and I filters. That's the camera. Here's the shutter, which kind of rolls here. The sensor is right behind that rectangle there. Finally, a moonlit photograph of me in the observatory, and that's pretty much what it looks like today. And it's open on over 200 nights per year, on typically 220 nights, and where, you know, I'll take 20 or 30,000 images. You know, it's not bragging, it's just what photometry is you take a lot of images typically. So, and then an acknowledgement section is thanks to my wife, Jennifer. Here we are out at the observing site, who's been very supportive through all of this. There's Mike Collins off on the right and me on the left when we were building the thing. And there's my mentor through all of this. Up speaking of Lowell Observatory, that's Brian Skiff, who's always been a real good liaison between professional and amateur community. And he's just been so helpful in getting me going on this and correcting all these errors that I've made along the way. So now I'm able to kind of go without his advice most of the time, but there isn't a subject that I can stump Brian on when it comes to instrumental astronomers, when it comes to people who are the observers. Here's the location of my observatory. I guess the profile of Arizona isn't very obvious here, but there's Phoenix, Tucson, Las Vegas. I'm located not even out in one of these sort of dark areas. I'm in the white area. And as I mentioned, I'm losing about 2.5 magnitudes to light pollution. But that's not a fatal thing for the type of work I'm trying to do, because that just means I can measure to 15th magnitude instead of 17th or 18th. I'll leave that to people at mountain top sites and at dark sites. And the observing site could always be worse. So here's somebody who also submits work to journals, and that's Richard Schmidt. And this is 2 miles away from the White House, and just in the, like, you couldn't imagine a much worse location. He images from this observatory in infrared wavelengths and is able to do some pretty good work. So, and there are plenty of sites that have worse weather. I have some of the best weather in the country. And what's really important for photometry to be able to do it night after night without worrying about too many clouds. So that's a real big advantage that I have despite my sky brightness. Okay, now we're into the next section, which is creating the images. A lot of this section will be familiar to people who do aesthetic images, who take nice deep images through various filters and hours of exposure. This will be real familiar to you. But these are all tasks that you have to do. You have to create a pointing model. You have to focus and do all your calibration frames and that type of thing. So just take a few minutes to go through what you need to do. One of the things that I do, I don't even know if it's every 6 months or so anymore, is you make a pointing model, which means the telescope will point to a field, and where does it think it's pointing based on how the telescope is pointing right now versus where it's actually pointing based on reference stars that you'll be able to get that position. And you do that, in this case, I've done it in 42 fields around the sky. And after that, it can make a model of all the errors in the mount, and you can end up having pointing accuracy that's well within a minute. That's within about a half an arc minute of the target every time. So the field of view of my sensor is 3/4 of a degree by half a degree exactly. And I always know that my target, no matter where I am in the sky, is going to be within an arc minute of the center, and that's plenty good enough. So helps with pointing, helps with tracking. What I also do, not nearly even monthly, so some of these slides I should have updated, is you want to make sure that you're in focus. This guy, Pavel Batinov, put this out on cloudy nights. He said, hey, I came up with this great idea for a mask. I don't think he patented it. I don't think he made a dime on it. And everybody went wild with it. And now you can buy them commercially, or people are 3D printing them. And an out of focus star, this line will be a little bit to the right. So out of focus either direction, and then there's software that'll tell you when you have perfect focus. That's one way to focus. Another way, if you're not at the telescope, they make these V-shaped curves that'll give the point spread function of the stars. And so you really want the focus to be good. The good news, and I'd highly recommend this if you're going to do any kind of imaging, is not to get an aluminum tube telescope. It's just worlds of different how much that aluminum expands and changes the focus through the night. So this telescope came with temperature compensation on the focuser, and I never use it. I can't see a difference under my seeing conditions between the focus at 30 degrees or 25 degrees, about as cold as it gets here, and 105 degrees. The carbon fiber tube is doing that well that I just unplug the focuser and don't mess with it anymore. And it's been great that way. Another thing you have to do is you make calibration frames. Like your system might have a vignette. So that means where the corners are darker than the center of the frame, and you'll have dust devils, little dust motes. So all the pieces of dust in the glass in front of the sensor or on the filters are making these little shadows, and you want to get rid of those. So there's several ways to make a twilight. You can make flats using twilight. So you can image the sky a bunch of times under twilight, or some people build light boxes, but mainly you just want a uniform light source and the right exposure on your sensor. I like this flat panel that I have. It's called an electroluminescent panel, and puts a really nice uniform light out there. And you just set it on top of the telescope while it's pointed at the zenith, and then turn on a light switch and do the flats that way. And so I do those every few days or so. Here's an example of what a raw frame looks like before I did the flats, or before I do dark frames or biases. Two other calibrations that you do that are actually quite a bit easier than the flats. And that's what it looks like as the raw image. And then here's what calibration does. So I know everybody likes pretty pictures. I do too, of planets or of galaxies, nebulae, that kind of thing. But even just a calibrated, simple frame of a star field that doesn't have dust motes in it and is mostly illuminated vignette, that's aesthetically, that's pretty to me also as well. So you also need to keep good time, because you're doing photometry, it's versus time. So I make sure that that the clock is in sync with a good, the clock on your phone is typically within less than a second, but there's software that you can get that'll set your computer and sync it up with the master clock. And that's a thing that you have to have as well. So I do, every night I plan the observations, or I'll do them a few nights in advance. And in this case, I'm going to observe 3 asteroids. And I use Sky Safari, which is this awesome, app that I use daily on my phone to find out when are they going to be high enough to start observing, and then when are they going to start to get to like 20 degrees or so above the horizon in the west. And I want to stop observing. and make a little table like this. And I make sure that I'm observing them when they're high enough, and I'm going to try to acquire the right amount of data to make these light curves that we're talking about. So this is a messy chart, but it has something that's sort of important, is that, believe it or not, the file naming matters. So these are year, month, date, object number and name, filter, and the universal time. And then that's a serial number that the software puts on the image back when I only had 37,000 images. So photometry, you're going to take hundreds of images every night, and you're going to look at various targets, and the scope's going to have to move back and forth, toggling between them. So you have to have a way to automate that, and you have to have a way to look at it remotely. So remotely, I use this app and software on a computer called TeamViewer. There are others. And what's nice about that is I can be out at the hockey game, or I can be miles away. I can be observing out in the desert, that kind of thing, and just look on my phone and check and make sure that the script is running properly, and see if that the camera and the images are coming across just fine. So it's a nice thing to be able to remotely see what's happening, even when the telescope is only in my backyard about 50 feet away from where I'm sitting right now. I like to be able to look at it from the computer that I'm working on without even having to go out there sometimes. And then scripting. So scripting is done, there's quite a few different packages that do this. Scripting just means you're automating pointing the telescope, setting the filters, setting the exposures, and activating the shutter of the camera. So in here, I'm going to take 2-minute exposures, and I'm going to run through all these targets repeatedly. So you want to have, it's like real simple-minded programming, like doing do loops, where you're saying, go and look at this, observe it 3 times, go to the next object, and then just toggle between those and loop, and then shut down when one object has gotten too low, and now just observe the other 2, that type of thing. So one of these software packages is called Sequence Generator Pro. Bob Denny here locally writes the best of these software packages. I use this real simple software called CCD Commander, which is great for the work that I'm doing. So after all of that is done, and believe me, it took a long time for me, especially to get to this point where I could get everything automated and learn how to do all these things, then you just press go. And that's the play button that's in the upper right that's circled, and it's going to run through the script. And at that point, I can go to bed, you know, and it could be, I can go to bed at 10 or 11 and have like almost a normal shift. And I can't wait to get up at 5 or 6 in the morning. That's just a bad habit that I have from working all those years, and look at the images. And they'll all be in a directory, 250 images, 300 images, ready to reduce that data. Let's take a look at a time lapse that I did with a fisheye lens of that telescope jumping around the sky. So there's 3 targets, 1, 2, 3, 1, 2, 3. It's going to do that for a while. The moon is pretty high. I imaged all but maybe 3 or 4 nights when the moon is near my asteroids at opposition. There's the dreaded meridian flip of this type of mount of a German equatorial. So you avoid that by getting a fork mount, which I couldn't afford at the time, a good one, and most of them are German equatorials. And now the moon is setting, and you can see that the sky is not really getting that much darker after the moon is completely set, but that's what I live with. So there's the whole script running for 9 hours and half a minute. Okay, you have all these images now, and now you have to reduce that data. And so here's a calibrated image, one of them. And I use this software called Canopus, MPO Canopus, and it's going to know by doing a plate solution, as they still call it, what the position, what the location of all these stars are that are all in a catalog, and even of the asteroid that I'm looking at in this case, which is circled in yellow. And here's a little time lapse of our asteroid slowly moving across the frame. Every morning that I get up and look at the images, I run a movie to know which frames I want to eliminate because clouds got into the frame, that type of thing, or just bad frames, something went wrong with the mount. And that's pretty rare, but I always run these movies to see what's going on. There's our asteroid's motion per the software. It knows where the first one is. in a half a night it's going to be there. So we'll see how that lines up. Here it is about 5 hours into the night, and target, and you do that. Once it knows those two endpoints, then it can measure the brightness. You can interpolate and measure the brightness for all of the points in between the start and the last image that you take. And the result of all of this is a light curve, as we said in the first few slides. And here is what is called a raw light curve. So I'm showing 7 nights of data, and this is of an asteroid rotating between those nights. And so each night, you're not going to continue when the sun's up. So you get 8 or 9 hours, 10 hours, I guess, in September. This is what you'll get. So obviously that corresponds with that. That corresponds with that. That's with that. And what you'd like to do is take all of these segments and fold them into a light curve, which is the repeating behavior of this asteroid as it rotates. And that's how you get a phased light curve. This is a real art of photometry, is getting to this point. So the software is able to do Fourier analysis and figure out that the period of rotation is almost 30 hours. The amplitude is about 4/10 of a magnitude. This is a very favorable asteroid. And there's our light curve. And that's what I would call complete for this asteroid. And you're probably wondering, why are there 2 peaks and 2 valleys for the asteroid? And I'll get into that in a little bit later. So I have talked for a half an hour about the process, which may be a little bit behind schedule. I usually like to do about 25 minutes on that and 25 minutes on targets. I'll try to not go too fast, but get through all the targets here. So there's something like 90 people in this meeting last time I looked, and if you really don't like plots, if you don't like graphs, it's a good time to go turn on the TV and ignore the rest of the talk, because that's what photometry is making plots of brightness of objects versus time. So I'll start with something that's real simple and common, and that's eclipsing binaries. And one of the first one that was ever known was Algol. And I hope people here have gotten a chance to at least look at it visually. Anytime that Perseus is up, I almost instinctively look at Algol and the 2 comparison stars and say, oh, cool, it's being eclipsed right now. I love watching stuff happen in astronomy. I'm not a big fan of just static images, but anything that's transient, that's an event, then I love that kind of stuff. Here's Algol. So Perseus kind of goes like that. Pleiades down there, Capella there. There's Algol. There's the comparison star that you use in Andromeda when it's at its brightest. There's the one at its faintest. So you can almost do naked eye photometry because it varies by 1.3 magnitudes. So that's in the bright prototype eclipsing binary star. What I ended up monitoring for a professional astronomer who was working at Northern Arizona University is called a contact binary. And this kind of dumbbell shape is saying that these stars are not even separated in space. They're actually contacting. And a light curve for a contacting binary looks like this. So when it gets up to its maximum, this is a phased light curve that's showing you every 4/10 of a day. So every 9 hours, 10 hours, whatever that is, you won't get a flat top anywhere because they're always contacting. You won't get a period where you're seeing the light of both stars steady. It's constantly varying. And then you will get a flat bottom when that smaller star goes completely behind the larger star and nothing is happening. So there's just a lot of information in there. And what Andy did was took my observations and some of his and some archive observations. And this sounds unbelievable, but as I've gotten more familiar with it, it's very believable that the period is increasing by 1.5 seconds every century. And that means something. Why is that happening? And that's what science papers are written on. And that's where I bow out and say, okay, you guys take it from here. I'm just an observer. And what I did for Andy was did this in 4 different colors. So here's these filters I showed you, B, V, R, and I filters. And there's information in here about why is that variation in red less than in infrared less than it is in blue. And that has to do with our red sunsets again. So we're back to that. and he can glean a lot from doing multicolor photometry. So that's one of the targets that you pick that's outside of the solar system. The one that's really a bandwagon topic that people really love is exoplanets. I decided to kind of not do that because there's a lot of other targets. There's just a lot of people have gotten into exoplanets. I think it's great. The first transit is only 18 years ago, so these haven't been around that long. And back in April, forgot to update this slide, sorry. That was the last time I did this talk. The tally was over 4,000 confirmed exoplanets. Now that we have the test mission through its engineering phase and doing observing, that's gonna just blossom. There's gonna be so many exoplanets and amateur work to be done on those exoplanets. So you get this piece of planning, not software, you get a website that allows you to plan and find good exoplanets to observe. So you want it to be bright, and 12.1, that's a pretty bright exoplanet. And you want it to not last very long, so that's 2.5 hours that it lasts. And you want it to be a deep transit. When that exoplanet passes in front of the star, you want it to vary by a lot. And believe it or not, 0.013 magnitudes is a pretty significant transit. So the illustration of what's happening in the one that I picked was that the star and the planet are about like the sun and Jupiter. But rather than taking 12 hours to go around the star like Jupiter does around the sun, in this case, the orbital period is less than a day, which is just hard to imagine a star and the sun and Jupiter and something that's way, way inside of Mercury's orbit, orbiting it every day. They call these targets hot Jupiters. And the light curve that you hope to get, the ideal light curve would be something like that, as this little planet passes in front and then dims the light of the star by a little bit, and then it brightens again. Here's what I actually got. I'm going to blow by this slide. And what I actually got showed the transit, and this was, I only tried this once, and I'm sure I could make this much better if I'd just worked on it a little bit. So here's the predicted middle of the transit, beginning and end of the transit. And you can see all I'm trying to show is that it really did dim by whatever it said, 13 thousandths or so, 10 to 15 thousandths of a magnitude. And then it brightened back up. And what you can see starts happening here is the star, the target, actually started getting kind of low in the west. And then those error bars that are shown here start to blossom. You start getting much worse results as it gets lower toward the horizon. One of my favorite things that I did spend a lot of time on, and may return to it pretty soon, is they're called short period pulsators. And before we get into them, I just want to make sure everybody's awake, because you can go to YouTube, and I'm pretty sure my presentation is more interesting than this. You can get 10 hours of paint drying, and this is an actual YouTube video that you can watch. So they're all at this Maya Bridge site. I highly recommend them. It's fascinating. So here's a pulsator, a short period pulsator on the HR diagram. They're just unstable stars, and that's all we really need to say about it in this presentation, that they're stars that are varying in brightness. The good news about these is that they have huge changes in brightness, like a magnitude, and then they have a period of like a half a day or a third of a day. So if you just want to do photometry of several targets in a night and get results right away and not have to wait for months or weeks or months, and you don't want the amplitude to be so small that you can't detect it, these are the perfect targets to start out with. One time, long time ago, I made this animation that's just 3 frames over a period of several hours of the globular star cluster, Messier 3, and every one of these arrows, and there's all sorts of other ones that are sparkling in here, every one of those is an RR Lyrae star in Messier 3. So pretty cool. I had no idea this was going to work as well as it did, but these are all variable stars. Now they're all beyond the range of what I can measure. These are all 15/16 magnitude and fainter, but just to give you an illustration, and they do that much over a period over only a period of several hours. So I think there was still useful work for an RR Lyrae star type of thing. And here's an example of one that's varying by a full magnitude, and it only takes 4/10 of a day for it to do that. So in a course of one night, you could get most of this light curve. In this case, I have 3 nights of data just to make sure it's kind of clearing it up, some of the errors in it. So among our Lyrae stars is something called the Blaschko effect. And I have a nice illustration that I did not create here that shows what's happening. So I showed that earlier light curve that I did, but many RR Lyrae stars are varying in amplitude, and then they vary in the shape of this light curve. They maintain the same period, but where that maximum happens varies from there to there. So these have been known since 1907, like just forever, but they're still not really well explained. And so the answer always is more data. If you're an analyst, you can't have enough of that. And the more you can gather, the better. So what amateurs do is you try to go out when a predicted maximum is going to happen and observe it for a couple hours on either side of that and compare your result to when the prediction was. So here's my photometry, are these blue points, and there's the prediction. So a prediction was too early, prediction was too late, and a prediction is spot on. This is my least favorite type because the maximum didn't show up at all in my data because the prediction was so far off. It was way too late. And so that's all I can give them in this case. And so what you submit to the professionals is, what did they predict? And what did I observe? Observed minus calculated. And that ends up being like, sounds like the most mundane data table you can look at, but it's the stuff that the pros have to work with. So you end up with something in the Journal of the American Association of Variable Star Observers, papers that are written by Jerry Simolik in Wisconsin. And he'll give you a table of everybody's observations, observed minus calculated. And then this is the Julian date. It's actually the heliocentric Julian date. And that's the table that you end up with. And here's all these observers, Jerry Simolik and Richard Sabo and myself, all these people who did this. And I haven't done this for a while, but I could see returning to it. It's real easy photometry to do. So if in case you wonder what the Julian date is, that's just a nice convenient way to take your date and just make a number out of it. You know, one date advances, and it put all these decimal points at the end of it such that the 5th decimal point is about 1 second, and you can keep going with those decimal points. So Julian date 0, if you want to know that, is, we're all the way up to 2,458,000. Julian date 0 was November 24th of 4714 BC. And I looked it up on the web and I found out that that was Thanksgiving that year. So yeah. So another thing is that we're in a moving target here on the Earth. You wouldn't think it would matter for stars that are effectively infinitely far away, but light speed is not infinite. So you actually do a correction, which is a bunch of math that gets done for me and I don't have to do it. If you're watching this star in June and then you're watching it again in September, that starlight is getting to you 10 minutes earlier than it did in June. And that's going to ruin your data. You want to be within seconds on this time of maximum. So you actually have some nice spherical trigonometry that's done to correct your observations as if you were sitting on the hot surface of the sun. So what I did a little bit of is 3-color photometry in blue, visual, and infrared. And here's a raw light curve for a star. And there's 3-color photometry, phased. I came pretty close to the published figure for what's the period that we go through in this particular RR Lyrae star. And there's a color magnitude diagram, which we won't sit on. What I got really interested in were double mode stars. And now this is getting really technical, but it's just so cool that the math can do what it does. So far I've just described these radial pulsating stars that just do that. But there are stars that are doing radial pulsations in 2 different modes. So there's not one period, there are 2 periods. Those combine, this is getting a lot like describing music, to make overtones. And it's kind of like sound waves with overtones. So what's the difference between those frequencies? What happens when you add one to another? That's going to make a really complicated looking spectrum. So when I first did one of these back in 2017, before I got just hooked on asteroids, this is what the light curve looked like. And it just looked random. It looked like, what is going on? How are you going to make sense out of that? And you can actually run an analysis called Fourier analysis, run software, and it'll give you these two frequencies, the fundamental and the first overtone frequencies, which are actually good for something because they can get plugged into this equation and make a model that's going to describe this accurately. That model is going to overlay if we do all the math correctly. So you just plug it into this equation here, which you should be well versed in by now. There will be a test at the end of the presentation. And here's 13 nights of observations, kind of a strip chart starting with May 18th, the 26th, and June 5th. Here's all these little segments of light curves that I got for NN Boötis. And I plugged everything into that equation and I made a spreadsheet, the mother of all spreadsheets, and worked on it, and trial and error, lots of error, but eventually I made a model based on those 13 nights of observations. And then this happened. And I just thought, this is the coolest thing. Math is beautiful. And you're actually able to model all of these convoluted shapes of this light curve where nothing seems to repeat. And just by doing that math and putting it into a spreadsheet. So that was kind of novel, and I still haven't published any of this yet and probably should have. It's been done before on other stars. So what I did then was said, what happens this year? That should read 2020, that's a mistake. So what happens if I come out in 2020, June, 3 years later with that same model and just blindly take this photometric data and it looked like that. So that's pretty awesome that 3 years later it hasn't fallen apart and it's still falling right on the model that I used. What all this reminded me of is if you look at a tide chart for a place along the ocean, you'll get similarly looking, random looking data. They're doing the same type of analysis to find out what are those tides are doing during versus time. My last target is the luminous quasar called Blazar CTA 102. If anybody asks me what's the farthest thing I've seen visually with my eyes in a telescope, it used to be about 1.5 billion years, 1.5 billion light years away, a quasar. Then the nice thing is that now it's 8 billion light years because this quasar reached 12th magnitude from that distance, which is just not even fathomable to me that something can be that luminous. And so I did some photometry on that. Back in 1964, it was suggested that it may even be an extraterrestrial civilization, and this got published in a Soviet journal back then. It's not. And here's my little animation time lapse of some dates monitoring that star, or sorry, monitoring that quasar. Here's my photometry, and it was going all over the place. Just as during a period of 1 month, it was going from 13th magnitude to brighter than 12th and then back down to 13th, kind of erratically. So Brian Skiff and I submitted this data to an astronomer, Claudia Ratteri, who's the principal author of that paper. And she wrote a big paper with, like papers are these days, with dozens of authors, and we got featured in there. And what's my contribution to that paper? And I should mention that, what's my contribution to this paper is that. And you can't even, I looked and looked and I still couldn't see my data points under there because I just measured in the V band during that little maximum, but still got my name in Nature. So my life is complete. I've been published in Nature. I'm good to go. Along the way, I made some variable star discoveries. This isn't really what I set out to do. I just do follow-up. I don't do survey work for discoveries. Here's a period analysis. What I did is kind of accidentally, but with the software, not accidentally, with the software, it'll tell you in a time series if something is varying, and almost always it's a cataloged variable star. But after doing enough of them, I was able to discover 7 new variable stars and then go out and measure them and report all of this to the AVSO. and it ends up in this index, which is kind of cool. So now you have an index that has my variable stars. And this couldn't be more trivial because surveys are being fed through a pipeline and thousands of variable stars get discovered and put into a paper. But I got to these before the survey, so that was kind of cool. Very recently, toward the end of last year, we had a very deep minimum of Betelgeuse. I hope everybody got out to see that because naked eye is just amazing. I didn't care if it went supernova. I knew that wasn't going to happen, but just seeing the star Betelgeuse become as faint as Bellatrix right across the top of Orion, it actually got fainter than when I took this purposely defocused picture with my SLR camera. It used to be almost as bright as Rigel, you know, at normal times, and it is a variable, typically only varying by a few tenths of a magnitude. So eventually I figured out, why don't I try some photometry? So my wife and I got together and made this professionally designed and manufactured aperture stop with 4 1¼ inch holes, 1¼ because that's the size of an eyepiece, and stopped down the telescope to these tiny holes and took very short exposures, a lot of them to account for scintillation, and did a light curve. So across the state from you is Tom Calderwood. I don't know where he lives. I think he's Central Oregon, but he's a prolific photometrist, and he uses not a CCD camera, but a superior way for bright objects like this, the photomultiplier tube. And here's his photometry in red, and here's my claptrap kludgy method in blue, and it sort of matches his, and that's enough said on that. If you go into the AVSO database, you'll see over the past 10 years, you'll see Betelgeuse doing this, dimming, 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 and then look what it did this time. So really can't wait to see what happens now that Betelgeuse is back up in the morning sky, almost at the meridian at dawn. I'm going to start monitoring it again. One more 10 hours. We've seen paint drying. Now we're going to see grass growing. I discovered this feature on YouTube that's very useful, that you can speed up a video so you'd only have to watch it for 5 hours instead of 10 hours. And that's a nice feature to have. And now this is going to be way too rushed, but what I'm doing most in the past few years, but might ease up on it, is asteroids. These are almost always main belt asteroids. A little bit of Sky Safari animation of where they are between the orbits of Mars and Jupiter. And they're all rotating, and people want to know what the shape of them. They want to know the rotation period of the asteroid and what's the shape of the asteroid. Best time to do it is in the winter. In the winter, the sun is low and the full moon is high declination for the northern hemisphere. That means that the asteroids at opposition are high. Worst time to look at asteroids is in June, when the asteroids are down in Sagittarius. This doesn't want to play, but that's okay. And then you don't get a long enough period to look at them, and they're compromised by looking through a lot of air, through a lot of atmosphere. So this asteroid, I'm going to go back to it one more time if I don't freeze this up. You can actually watch this asteroid dim versus time. And that's pretty rare, that the magnitude changes enough that you can see it change in these time series. There's a phase light curve based on all these nights of data, which I showed earlier, 29 hours. And if you do this on 3 different oppositions or more, and you're really good, you can make a shape model of the asteroid. So I told you that I was going to try to explain why are there 2 maxima and minima, as it does only 1 rotation. Well, the elongated, they're almost never spheres. So there's a maximum, minimum, maximum, and another minimum. And there's the corresponding light curve. So that's the kind of thing you can actually make a faceted model of an asteroid based on amateur photometry taken at 3 different oppositions. This is another one. Not only do you get these, you don't get regular curves, you actually get little steps like that, where it hits craters and mountains, that kind of thing. I guess you'd call them mountains on an asteroid, even though it's a rubble pile. And finally, this one, which is really cool, this already had a shape model made of it, and I'll let it run a couple times. Then people went out and watched that same asteroid pass in front of a star and do an occultation from various stations. And those are the paths that they got. And the match was amazing between the shape model that already existed and then this verification by a completely different method of going in and measuring when did the star disappear behind the asteroid and when did it reappear. And this was done by mostly people in Arizona. David Dunham is now in Arizona, and these people. So pretty cool. So there are journals for pretty much everything. There's Science to Fuzzy Systems, Flavor and Fragrance. So they got journals for pretty much everything. So you got to have some kind of asteroid journal out there, and that's called the Minor Planet Bulletin. And so that's who I submit to. And here's the first time I ever did this. Brian Skiff did the measuring. I just submitted images to him until I eventually learned how to measure them myself for 2 asteroids, Helio and Demeter. They were both pretty easy targets, and that was a lot of fun. So since early 2016, which is getting on 5 years, I've done photometry of 215 asteroids and found period solutions for over 200 of them, and actually hopefully corrected, didn't make it worse, and found either new periods or corrected previously published periods for almost 100 of them. And now it's 15 Minor Planet Bulletin papers that have been published. So that's been my singular focus. Again, I might ease up on that now that I see what's happening in the field. So not only the Minor Planet Bulletin, but also at astronomy and astrophysics. This is Anna Marciniak and a bunch of co-authors. She's in Poland. They have a big interest in photometry of asteroids and in doing shape modeling, figuring out more about our solar system without sending spacecraft out there. So a couple interesting results for asteroid light curves. Before we really get to those results of photometry, I made this little canned example in Excel. Here's a example of one with a rotation period of 33.5 hours. So night on Thursday, you'll see that. Friday, you'll see that. Here's a couple cloudy nights. Monday, we always see something different happening with that asteroid. And then we can fold it together and make this beautiful light curve. Again, this is just an example to illustrate what I hate is when an asteroid has a period of 24 hours, because that means you just see the same face of it every night that you go on, because we're bound to the planet Earth here, and we also rotate every 24 hours. If you've been observing Mars, you get almost the same problem. Luckily, Mars is not exactly 24 hours, and it backs up a little each night. So here you would just keep getting that. You would do a phase light curve, and you're missing all of that. So the only solution there is to collaborate with observers that are in Australia or in Europe that are at other longitudes. But since I don't play well with others and I've had bad collaboration experiences, I just give up when that happens. There are a couple good collaboration experiences, but mostly we just do things differently. Another problematic case that you can have is that it's called the gray cue ball. It is a sphere and it doesn't have any features on it or albedo changes. So you go out for a couple nights and you just get the same thing. You go out for 4 or 5 nights, you just keep getting, that's just errors. So you're not seeing any amplitude. So you got to know when to cut bait on those. This is one where I didn't cut bait and it has an amplitude of a whopping 5/100ths of a magnitude, but still good enough to give me a period, even though there's all this scatter in the data. Brian and I observed a real long period asteroid. It has a period of a couple weeks. And not only does it have a long period, and this is not that uncommon, it's tumbling. So you don't get the same light curve every time. Tumbling means the axis that it's spinning on is also tumbling over. So you're going to get different features every time. You'll be able to get the period, but that's confounding the results, and you can't necessarily get that tumbling period. Frederick Pilcher and I, this is one of the most observed asteroids ever by 2 individuals. We got 5,000 data points over the course of over 3 months to get this rotation period of 18 days. And then same thing happened here where you know that it's tumbling, but you can still get a really solid handle on the rotation period. And the longest, mine is the 3rd longest in the entire database, is this amazing one, 2056 Nancy, named after Brian Marsden's wife. It has a period of 1,343 hours. So that's nearly a 2-month period for this to rotate. and it's just a little, 20-mile, 10-mile diameter rock. So what happened to cause that? And we had this remarkable set of photometric of clear nights. 52 nights out of 58 were usable to do this light curve back when I was observing it. And it's pretty amazing. Another example, and this was the only one of these discoveries I've been a part of, is Brian Skiff and I both observed this one, and we couldn't make any sense out of that. You couldn't fold it into a phased light curve that gave you the period. And so we passed it over to the guy that you go to, Peter Pravich in the Czech Republic, and he's able to make sense of it. And the reason that it makes no sense is that it's a binary asteroid. And it gets even better still that there's these eclipses, and I swear only Peter really understands this, and he was able to show that it very likely is a three-body asteroid, that it has a third one. So we got an electronic telegram published, and it has our names on it. There's Peter did all of the calculation work, and he very carefully writes that it's possible that there's a third body in the system. It says that this suggests that, but you don't want to be definite and find out that you're wrong. So I have taken tens of thousands of images, and I'm right at the end of the presentation, right at an hour. Took a little too long, sorry. And I've taken tens of thousands of images, even over 100,000 now, and you find interesting stuff. I haven't found any UFOs on the images. Those are just blooms from the CCD camera, but found some other stuff on the images. One of the bad things you find in the image is clouds. So this is why I run the movie every night or every morning after I gather the image. I don't know how cloudy it was when I was sleeping. Those are the cirrus clouds that we get in Arizona at the southern edge of fronts, where it's raining in Portland in the winter. It's just cirrusy here a lot of times. So satellites are very commonly found on these images. If you ever want to get me started on something, just say the word Starlink. So that's not my favorite thing in the world, even though even amateur astronomers are justifying this amazingly. So, and there's airplanes. I'm 7 miles away from Sky Harbor Airport. This is pretty rare that they fly overhead, but once in a while they get diverted over our house, and there they are. And other asteroids are pretty common. So here's my asteroid that I was observing on the first of the 3 nights. And here's 3 other asteroids. This one's really faint. So you find that in your images as well, which is kind of cool. And if it's bright enough, you can actually measure it as well. Neptune was one time on my image. So there's my asteroid, Orelskaya, and there's Neptune with its moon, Triton, hanging off of it right there at 5 o'clock. Galaxy cluster, I get deep sky objects every once in a while. And you can actually stack the frames and make a pretty decent deep sky image out of it, because you're shooting the same frame every time while your asteroid streaks across. I found an eclipsing binary star once. So I have all these comparison stars. What you're seeing there is just the rising and setting of the star, and then there's the eclipse. It ended up being a catalog star. So, and finally, I made mistakes along the way. So, classic phrase, mistakes were made. And so we'll close with a few of those. My filter wheel used to lose its mind once in a while, so I'd get up at 5 in the morning all hopeful about what I got, and I'd have 250 images that look like this, and not very good. My mount a couple times didn't want to correspond, didn't want to talk with the software, and so you get 6 hours of images of just star trails. I've shown you the Batonov mask, which shows you when things are in focus. A couple times I've left that on for 4 or 5 hours and then realized, oh, those are not going to be really good images. Sometimes, pretty rare lately, I have this happen. I run the movie and I look for my asteroid in it. And the reason that it's not in it is because it's somewhere over there. And then sometimes I run the script too long, and here's what stars look like when they're setting over my neighbor's tree or over our orange tree. So lots of mistakes can be made. Finally, the good old explosion at the donut factory. I've just unplugged my focus because a couple times my focus would come partially unplugged and then decide to defocus everything. So we're down to the last slide. I went over. I hate it when people go over, but here I am doing it. And the last slide of the presentation has to be another plot. And this is the plot of your interest in this presentation, your declining interest. It started normalized that, well, every presenter starts at 1, I showed a sports car, so I peeked a little bit and showed the Simpsons. And then I went down to there, and then I announced that I was at the last slide, and here we returned back to one. Thank you so much for sticking with me, and sorry again for running over. That's my talk.
Thanks, Tom. That was very, very nice. If you have questions for Tom, please enter them in the chat.
Okay, so
And Tom, if you peek at the chat, you're getting some nice feedback.
I'll do that now. I'm trying to figure out how I get it back. I guess I unshare the screen. There we go. Yeah, that works. All right. And then
So, and I can read the questions to you, or you can read them yourself.
all righty.
Kind of up to you.
I'll read them, I guess. So
All right.
let's see. I'm going. Oh, it has nothing to do with respiratory disease. All right. Let's take a minute. Almost
Yeah.
sorry.
Should I give you the first one?
Yeah, fun humor, fantastic. All right, thanks, great talk. Oh, how did you measure the magnitude of Betelgeuse? Is that the first one?
Yep, that's the first
Okay, that is a 15-minute talk in itself, and I'm all talked out and you're all listened out, but that makes ensemble photometry difficult. That's a real good question, because you can't have a first magnitude star and then find first magnitude comparison stars in a field that's a half degree across, right? So what I had to do was old-fashioned photometry of panning this telescope, writing a script that goes over to Aldebaran, which has a similar color and is stable as one of the comparison stars, and then a star up in the head of Orion, the Orionis, was the check star. And that would show you that your results were stable over time. So you had to do a lot of images of Betelgeuse, a lot of that, and I did it in several sets, such that you can do something that's not an ensemble, that's like old school photometry that Tom Calderwood is doing with the photomultiplier, which is doing the old way, that photometry. And that was a good lesson in how to do that. All right, somebody's going to go watch paint dry. All right, talk. Is living the dream as good as you hope? Yeah, it's really better. I would say that it's, and this has happened to a lot of people who have backyard observatories, is then you stop going out with your buddies observing as much. You stop going out to dark sites and observing. And my wife is in particular not very happy about that results, that we don't go out nearly as much as we used to observe in the desert. I can always come up with excuses, and that's not a good thing. So yeah, so that's where that ends up going. But as far as how that's gone, that part of my life just couldn't go better. I mean, that's really been keeping my interest. I'll say that asteroids are my work, I think, is going to become obsolete in the next year or two, at least just getting basic light curves of main belt asteroids. There's still subtopics in there, but that's just, the surveys are getting so comprehensive. Even before the telescope used to be called the LSST, Vera Rubin telescope, comes online, that's, I'm already seeing it happening. Okay, how did you get started submitting data? I talked to Brian Skiff, who I can't give enough credit to as my mentor through all this. He told me where is the best places, or who's the best astronomers to talk to about various subjects. In a couple of cases, like, I would just look them up. One of them is from my alma mater, from Michigan State University, who got into double mode RR Lyrae stars, this little niche, and that's, everybody's a specialist these days. So you can just kind of look them up and then email them and say, I'm just an amateur, but here's the stuff I'm doing. Can you help me along? So it's kind of how I've submitted stuff. So have you known anyone who has taken an 8x10 standard home shed and created a backyard observatory, changed the roof to a roll-on, roll-off? It seems like you could do that. I've seen people modify them, like you put a big counterweight and the entire roof kind of goes off like that, kind of goes off on a pivot. I've seen that type of thing, but not seen one modified that way. This was very much an observatory the whole time. If we ever move out of this house, then somebody will have a shed with a roof that rolls off if they ever want that. With surveys becoming so comprehensive, where are the areas that we as amateur astronomers can focus our efforts and continue? I hope I showed that in this talk, because you see how compromised my site is, even though I have a lot of clear nights. But the surveys are have always been a problem. I mean, was it 20 years ago, amateurs used to routinely find comets. And now in the last decade, there have only been a few, like Don Machholz, there are just a couple people who have discovered comets because they're all getting swallowed up by the surveys. And the surveys are now used for photometry. What you can do, though, that the surveys can't do is real rapid cadence photometry. I'm going to take over the course of one night, I'm going to take 300 images, and I'm going to show with a time resolution of 2 minutes, I'm going to show the behavior of this star. Surveys tend to jump around the sky, and then they pull all that together after a month or two, or after a year of observing, of hitting the same target, which wasn't really the target, it just was in the field that they were looking at. So what I can do better is do real short-term kind of variations that happen in stars. So that's one of the ways that you can sort of defeat the surveys. But like I said, the asteroids are going to be really difficult. Highest latitude observatory of similar setup right at your latitude is Tom Calderwood and others who are doing science work. What was his name? So there's somebody who was affected by the fire, I think, is doing spectroscopy. I know there's somebody in Oregon who is doing spectroscopy. Was that Sean? I thought his name was that. But anyway, yeah, so there's people at your latitude, and there are people in Canada. And as usual, this is not a patriotic or anti-patriotic in any way. The Europeans are kicking our butts. And that's always been the case, that when it comes to this type of work, especially spectroscopy, a lot of that's being done in France, and all of Europe is 10 degrees north of all of the United States. If you are, I mean, the centroid of Europe, if you will. So they're located at 40 to 60 degrees, and it's not stopping them from doing science. So I think it can be done. One of the things you could do if you had a real high latitude is you can follow things below Polaris, which I can't do because Polaris is only 33 degrees above the northern horizon. But as you go farther and farther north, you could follow a target or observe targets that are below Polaris that you wouldn't be able to do if you were closer to the equator. There are not many advantages being toward the poles, but that's one of them. Okay. I had a question I think you overlooked in that slide where you showed where the asteroid you're tracking was off your image. Lots of little dots sparkling. Those dots are all because I'm not doing real good dark frames, and there's random cosmic ray strikes. So anytime you run these movies, if you look at a finished image of a pretty picture kind of image, typically now they're stacking 20 frames, 50 frames, whatever it is, and all that stuff is averaging out. But if you do, all of those are individual frames in that movie, they're not stacked. And so any kind of little defects like that are going to cause this kind of sparkling of the image, which you get over. It actually doesn't hurt the photometry. Ever run out of computer storage in the process? Fortunately, I'm shooting binned 2x2, so an entire night of images is only maybe 1.5 gigabytes or so. Recently, with my 15-inch Dob on a platform out in the driveway, I've started doing planetary imaging. That's a different story, because then you're recording video, and now I'm coming away with 10 gigabytes, 15 gigabytes all the time, and that's how I'm going to run out of storage. But fortunately, external hard drives have become very affordable, and so it's not much of a concern at all. Is the work in Europe also being done by amateur astronomers? No, that's amateur astronomers in Europe. So we have some of them, and especially of all places, England, which can't get much worse. They're way up 50 degrees, 55 degrees north latitude, and their climate is horrible. And yet there's a lot of people in England, like I said, France, Italy, they're doing this type work, and they're amateurs. And it's just a culture difference or something that the Europeans for a long time have been more prolific at this type of work. It's not a criticism, that's just what I observe or what I've been seeing for years and years, that's how it's going right now. Are you doing scientific work with your imaging of planets with your Dob, or is that's very much for fun? Sometimes it's not that fun when things stop working, but that's one thing that people have done in the past month, 3 different amateurs have discovered storms on Jupiter. And I've imaged all 3 of them. They're all at the same latitude in the northern equatorial belt. And all of those are discovered because what professional is monitoring Jupiter, for example. And so they've been real easy to observe and to image. I'd like to discover one of those someday, but I'm not up there with those people observing every night. So just 2 nights ago, I put this image out on Facebook and nobody seemed to care, but I thought it was just really cool. Was the same camera that does the right exposure for Mars, you know, a 50th of a second. If I crank the gain up real high and do a 1/10 of a second, the same camera got Phobos and Deimos easily by doing a little bit of processing. So I took 6 images of that and did a time lapse that shows the 2 of them where they are exactly where they should be in their orbit, which, you know, the same camera, these color cameras, it's a 1-shot color, have gotten so good that they can hit 13th, 14th magnitude now. So the brightness of Phobos is 15, or Deimos is 15 magnitudes fainter, a factor of 1,000,000 fainter than Mars. And that camera can record Mars and make a stacked image and record those satellites. So cool. You ever do high-speed variable target? There must be some photometrists on, on this list, people who are familiar. I haven't, like AR Scorpii. That sounds like a good idea. And like I said, I'm kind of overdue to get off my fixation on asteroids. And so these are good, that's a good suggestion, is that kind of thing is what I need to move on to. But from my backyard site, I can only go reliably. The errors start to explode if I get fainter than about 15th magnitude. So that's kind of where I'm limiting things. I like to keep the exposures down to a couple minutes and keep them short. I can do real good photometry out to about 15 or so, to V15. And then after that, it's these people who have 1-meter telescopes who are out at real observing sites, not Phoenix. Okay, and I'm signing off. Good night. Okay, good night. And okay, yeah, I think that's the main questions that were on here. It's really cool. If anybody, I mean, I'll put my email or address, or I'll send it to Mark or Margaret or whoever. And if people have offline want to ask a question, or if anybody wants to get started in this, that I'm happy to correspond with them at all.
So I had one other question for you,
Oh, yeah.
Tom. So I was wondering if there are proportionally more RR Lyrae stars in globs than in other locations?
Yes.
And if you would know why that.
Yeah, and no, I should know why, because I just spent so much time observing them, and I should know the answer to that. The only reason I show that animation, other than it worked out way better than I ever thought, was somebody said, of all the globulars point at Messier 3, and of course that passes overhead from our latitudes, just point at that and try a time lapse. So I took only 3 different times over a period of several hours, and there must be hundreds in that globular cluster. And why that would be, that's a good question. I just never gave it any thought, and there's probably people in attendance in this meeting that know the answer to that. There we go. I see something from Mark Lowenthal. Globular clusters have stars old enough and evolved enough to be RR Lyrae. That's great. There it is. There's your answer.
So they become unstable as they get older.
They're evolved enough. Yes. They're at that point in the color magnitude diagram.
Cool. Thanks, Mark. Well, any more questions for Tom?
So one other comment. So I heard somebody in the beginning say something about, is it 575 members? Like our membership's not that impressive. So this is the reason Phoenix is lame, is we have 3 astronomy clubs here with a little bit overlap of members, and about 250 in all 3 of those, in a city of 4.5 million, and in a climate that we enjoy in Phoenix. So, and we've tried. So I'd like to talk offline with somebody. What are you guys doing? I mean, I know you meet at a science museum. That helps a lot. But yeah, 250 or so. Though the biggest one's the East Valley Club with about 125. So our astronomy club is literally dying. It's pretty sad, but that's been a great club, and it has maybe 70 now. And the Phoenix Astronomical Society is another 50 or whatever. So, and that's it. And so why don't we have 1,000 members and and a huge budget. I don't know.
It might be that we don't see the sky enough and it makes everybody really long for it. So they want
Could
to.
be. There you go. Oh, don't know.
So there
Tom,
is,
do you want me to put your email in the PowerPoint that I showed, and then we upload it to our website and people can get in there and get a link to you?
Sure. So yeah, that sounds fine. Yeah.
The one that you corresponded with me on, or do you have a different one?
Oh, that's the one. That'll work. Yeah.
Okay.
Put it out
All
there.
right. I will include that.
so there was a suggestion about membership. I guess someone was suggesting that maybe more outreach would be.
Yeah, and we do a fair amount of school star parties, or did until this happened this year, but we were doing at most like a couple, 2 or 3 per week for the entire school year. And then that's kind of tapered off. The person, you have to have a really dedicated individual who wants to do that, and it's tapered off. And that helps the membership enough. But yeah, it's always been kind of a problem here.
Well, and that's another advantage you actually have over us because we typically can't do star parties during the school year.
Right. Yeah.
Why is that?
Well, because of the clouds.
Oh, because
Clouds roll
school year's
in.
running. Oh, all right.
Yeah.
Yeah.
Yeah. Tom, one thing that I think has worked for us is, and I can give credit to Paul for this, is that he really pushed us to get onto social media and to use it right, because there's nothing that looks more doofus than an old person using Instagram and not knowing what they're doing.
Yeah.
Or somebody saying, oh, I'm afraid of Facebook or something like that. Younger people, that's how they communicate, and that's how they find each other, and that's how they find who they want to meet up with and hook up with and learn from. And so if you can find somebody younger who's really pretty savvy with social media, you will begin to get younger people.
Okay.
And
We have a real good Facebook site for the club, especially for the EVAC club. For the next door to where the EVAC club meets is a riparian center that has an observatory with a 16-inch telescope on a paramount that's used every Friday and Saturday night for outreach. So there's a team of people from EVAC who do that, and then it's paid for by the city, and then we run it. And that's passed through 100,000 people after about 5 years, 6 years in existence. So you would think from that, and it's been amazing how successful that has been. And it's just people see a dome, hey, I wonder what's going on here, and they go to that. So we have, in EVAC, we have a Facebook, but we don't do any Instagram or Twitter or anything. And like you said, that kind of requires youth, which is sadly lacking in the entire hobby these days.
So there was a question from Stephen. He asked what minimum aperture you'd recommend.
6 or 8 inch, something like that, I think. So aperture is going to determine how deep you can go. Those RR Lyrae stars are sometimes 12th or 13th magnitude. So you could do that with an 8-inch scope or so, just fine. So I think you could do that. What I'd be the most concerned about would be a reliable mount, a mount that's going to be able to slew across the sky a lot of times and not fall apart and be able to, run a script on it, that kind of thing. Or you could not even run a script and just follow a single target through a night, and that script is real simple. It's just keep taking the same exposure over and over until the object's getting ready to set. But I think you could get by with I have a 12.5. That's not a huge aperture. I think you can do fine with 6 or 8 inch, but you just want to have a good, reliable mount and a reliable camera. And it's too bad because I went through a lot of iterations with the Celestrons and with the Meads and with those are perfectly good telescopes, but when you start taxing them this way, they sometimes don't hold up, to put it nicely. And so I just finally said, this is the entry fee to this type of level of sophistication. I have $40,000 and I'm going to spend it 3 ways: telescope, camera, mount, and divide that 3 ways. And that's what it cost me. It doesn't have to cost that much, but you'll find that's a pretty common for people doing astro imaging with large telescope or medium-sized telescopes. I hate discouraging people, but that's just kind of how it ended up working for me after a lot of frustration. And so one of the bits is a mirror that flops around, and you can't have that. You can't have that mirror. You got to have an amount that's not tight, that kind of stuff, and the camera that breaks. So yeah, unfortunately that's where it is. And I have a pretty big bill coming up because I'm probably going to abandon this CCD camera in a couple of years after all the photometrists have sorted out what CMOS cameras do. And so I'm so comfortable with this camera, but eventually I'll switch over from CCD to CMOS, and that's going to be a big bill. But I will say, since I've had it, I have made almost no astronomical purchases because I'm set for visual. I'm not a real good consumer. I like getting comfortable with something and just using it and getting results. And I don't care about the consumer side of the hobby. Once I bought that and put all that money down, I don't even look at the ads in the magazines or anything anymore because it just keeps going. So that's been a good thing. It's a one-time expense.
So I think there's one more question. I think we'll let this one be the last one. And Mark was asking if it's true that anyone who does imaging can do photometry as well.
Yes, and you could you'd want to get like maybe 3 of those photometric filters, but if you're doing asteroids, I don't think I mentioned that. I use a luminance, a clear filter for the asteroids just to get the maximum signal, and I'm able to do that because the color doesn't change in an asteroid as it rotates, right? So if the color is changing, you can't image through a clear filter. You'd have to have one of these narrowband filters. So with just a camera, even a CMOS camera, if you really know what you're doing, like a webcam kind of thing that you can do planetary imaging with, if you have a sort of reliable mount, scope, and a CMOS camera and no filter, you'd be able to do bright asteroids, and you could do exoplanets. That doesn't have to be filtered. You'd be able to do some types of targets because the filters are going to run about $200 each typically. So if you can do imaging, you can do photometry. That's the correct answer to that.
Thank you very, very much, Tom. It was
Yeah.
very nice having you come and speak to us, and really enjoyed your presentation.
All right. Thanks, guys.
So please join us next month. Next month, we'll have a related talk. We heard about characterizing asteroids this time. Next time, we'll be hearing from Professor Vishnu Reddy from the University of Arizona, and he'll be telling us about planetary defense and the search for killer asteroids. So that should be a nice follow-up to Tom's presentation. I hope all of you have a great month. Thanks for joining us, and we'll see you next month.
Yeah.